Good morning, I am Renu Sharma, Assistant Professor EC Department. Today I am going to start with the next topic of this subject, that is wireless and communication, and the topic of today's lecture is diversity techniques. So these are the contents of today's lecture. First we will discuss what is a diversity technique, means its introduction. Then different types of diversity techniques are there. There are basically 4 types of techniques. First one is selection combining, threshold combining, equal gain, maximum ratio, then spatial and multiplexing in MIMO system. So this is multiple input, multiple output system. So this will we are going to discuss this topic also. So I will begin with diversity technique. So diversity techniques are used for improving the reliability of a message signal by utilizing 2 or more communication channel with different characteristics. So what do you mean by diversity technique? It is a technique which is used in multipath propagation. Let's say there is one transmitter and one receiver is there, and no direct line of sight exists between the transmitter and receiver. So this particular signal has to propagate from this terminal to this terminal via different path. Means in between this there are different factors that may affect the quality of the signal. It can be scattering, diffraction, reflection and refraction. So these are the 4 parameters which will going to change the characteristics of the signal. Either they can increase the strength of the signal, they can decrease the strength of the signal. Also attenuation can take place, noise can be added. So this will basically change the quality of the signal which will be received at the receiver side. So since multiple signals will be received through different multipaths, so these signals will be combined together at the receiver side. So there are different ways by which we can consider the received signal. Either we can combine those signals which are received having different characteristics, or it is possible that we can consider each signal individually and we can select the maximum strength of the signal which is having maximum strength. So this is the main idea behind diversity techniques. So multiple version of the same signal may be transmitted or received and combined in the receiver. So that's what I have said, that it is possible that either initially I am going to generate multiple version of the signal that can be transmitted, or due to multipath propagation multiple versions of the signal will be created on its own, because the signal can travel from different paths. So in this figure which is given over here, the different independent fading path are shown with different CIR, that is carrier to interference ratio. And carrier to interference ratio we can also consider signal to noise ratio also, but this is more prominent over here. Means carrier signal, the signal which is being transmitted divided by the interference, which will going to affect the quality of the signal. So CIRs H1 to HNT, and the distortion in the signal is observed due to addition of interfering signals, that is I1 to IN and white Gaussian noise. So you can see that this is the signal that you want to transmit. Now these are the multiple paths. Let's say I am going to take 4 different paths. So this N will become 4. So here will be H1N, H1T. It is continuous time, so I am taking it T, H3T and H4T, which means 4 different paths will be followed by a single signal. Now it will be added with the interference that will going to change. This will again, it becomes 4. Then in between this there will be I2, I3, and here it will be I4. Then it will be added with a noise that is known as AWGN, additive white Gaussian noise. Now at the output side, this will be the received signal. So signals used for combining and equalization purpose. So whatever signal, this will be the transmitter side and this will be the receiver side. Now here 2 options will be there. Either I can combine these 4 different signals, or I can consider these Y1, Y2, Y3, Y4T as an individual signal. So, this is the way of designing a diversity model. Now, the strongest signal is then picked from the received signal. So, this signal can be further equalized and demodulated to receive the digital signal with minimum bit error rate. So, whichever signal is having the minimum bit error rate, that is, let us say I have transmitted 5 different bits, and in 5 different bits one bit is being is having an error, or there is another case that 10 bits has been transmitted and 2 bits are having an error. So, that is how we can calculate the bit error rate value. Now, diversity combining is the process to extract the main transmitted signal with minimum channel effect out of many version of the signal. So, let us say 4 signals are received at the receiver side. So, whichever signal is having the minimum bit error rate, which means it is having it will be less affected with noise, then that signal will be considered as the received signal. Depending on the type of fading, diversity technique have been characterized as 2 types of techniques are there: micro diversity and macro diversity. So, in case of micro diversity technique, these techniques are used in a small scale fading environment. 2 antennas are separated by a fraction of a meter. So, there are 2 types of diversity depending on the area which is to be covered, means which is to be considered between the transmitter and receiver, means the distance, you can say. So, this is the transmitter, this is the receiver antenna I am considering. So, whatever the distance is there, let us say I am considering it as d, d is the distance between the transmitter and receiver. Then in case of small scale fading, this micro diversity technique is used, whereas in case of large scale fading, when the distance is quite large, in that case this macro diversity technique will be used. So, this is the these are the 2 different types of techniques that are possible. Different diversity techniques means although it is dependent on the area which it will going to cover, we can also divide using the antenna or the relationship between the different signals that has been transmitted. So, first type of technique will be the space diversity. So, in this case of space diversity, it can be microscopic, it can be macroscopic diversity technique. Space separation of half of the wavelength is sufficient to obtain the 2 uncorrelated signal, which means that in this case the distance between the transmitter and receiver can be considered as lambda by 2, where lambda will be the can be calculated by the frequency of operation, means the frequency of the signal which is considered for transmitting the signal. Now, this is sufficient enough, this lambda by 2 is sufficient enough to obtain 2 uncorrelated signals, means in this case let us say 2 paths will be there. So, in 2 multipath will be considered. So, this can be lambda by 2 is sufficient to receive the correct version of the signal at the receiver side. Next one is the polarization diversity. So, obstacles scatter waves differently depending on their polarization. Antennas can transmit either a horizontal or a vertical polarized wave. When both waves are transmitted simultaneously, received signals will exhibit uncorrelated fading statistics. So, in this case, in case of this polarization diversity, the signals will be transmitted depending on the polarization of the antenna which has been there. It can be vertically polarized, it can be horizontally polarized, whichever polarization you can consider for the diversity. Next one is the angle diversity. The received signals arrive at the antenna via several paths, each with a different angle of arrival. The signal component can be isolated from the directional antennas. So, depending on the angle which is being covered with the antenna, let us say there are this antenna I am considering, this is a directional antenna and this is the region which it will going to cover as a maximum lobe. So this is the angle, and let's say there is another antenna which will going to covered in this angle. So whatever angle I am setting of this particular antenna will going to decide the angle diversity, which will going to decide the quality of the signal which will be received. Next one is the frequency diversity. So information is transmitted on more than one carrier frequency, because the frequency separated by more than the coherence bandwidth of the channel will not experience the same kind of fading over here. Next one is the time diversity. Multiple versions of the same signal are transmitted at different time instance. So what is the main difference between frequency and time diversity? Let's say there is only one signal that you want to transmit, and you are generating different versions of the signal by considering different time instance. So that is the time diversity, and when I am considering the different frequency instance, then that is known as frequency diversity. Next one is joint diversity. So combination of above mentioned techniques. So any of the 2 or 3 techniques can be combined together to generate a joint diversity technique. Next one is diversity combining techniques. Now we'll focus on different types of space diversity techniques. First one is selection, then threshold combining, maximal ratio, and equal gain combining techniques are there. So these are the different types of space diversity techniques that exist, and we will going to discuss it with separate block diagrams. First one is the selection combining. So this is one of a kind of space diversity technique. So it is based on the principle of selecting the best signal, the signal which is having the largest energy or the signal to noise ratio. So one thing you have to keep in mind while considering the continuous time signal, that you have to consider a parameter, that is signal to noise ratio, which means the signal which is having maximum signal power divided by noise power. So this is known as signal to noise ratio, which is equivalent to SNR, signal to noise ratio. So among all the signals received from different branches, so let's say this is at the receiver side, we are considering a model where different antennas are there. So these are the different antennas that are considered, and at the output of every antenna there is a gain factor is there, means each branch as having their different gains, that is G1, G2 up to Gm. So this will be the first gain, second gain, and Gm. Now this will be passed through a demodulator, that is switching logic or demodulator will be there. Now whichever, let's say it is having a signal to noise ratio 1, it is having a signal to noise ratio 3, it is having a signal to noise ratio of m, whatever number of branches we are considering. So there are m different number of branches are there. So these are having the different signal to noise ratio. So this is to be passed through a switching logic or demodulator will be there. Now that will be passed, it will be received at the output of this particular filter. So this is the selection combining technique. Next one is the threshold combining. So threshold combining is a special form of a selection diversity that is less expensive to implement. Here a limited number of signals are considered for the extraction purpose using a threshold level. Scanning and feedback mechanism are used over here. So let's see its detail in this particular diagram. Now you can see that there are 2 antennas. This is antenna 1 we are saying, and this is antenna 2. Now the signal will be received at both these antennas, and there is a switching control which is been connected over here, which will going to select, this is simply a switch which will going to select any of the antenna, either this antenna or this antenna. Now this antenna the signal will going to receive, and then this will be the receiver, and the signal will be transmitted, it will be connected to a short term average of short term average, means the average of these two signals will be considered over here. Now there is a comparator, the output of this will be applied to a comparator which will going to compare this average, the average of these two signals will be compared with individually signal, and whichever signal is greater than threshold, that will be considered at the output side. So this is how we are going to work in case of this threshold combining. Now next comes the equal gain. So as you have seen in this particular first selection combining, there is different gains that are considered, means there are 10 branches are there, then 10 gain values you have to consider. So this is very cumbersome and it is not it is not very easy to consider systems having different gains. So what is being proposed in this particular thing, equal gain, that each of the branch is having single gain, means only one gain we have to consider, but there are m number of branches that can be considered. So equal gain combining is better than the selection diversity and is almost as good as maximum ratio combining, but is less complex in terms of the signal processing and feedback part. So the idea behind this technique will be clear from this particular diagram. Now you can see there are m number of branches. So let's say I am taking 10, so m will become 10 now. So there are 10 different branches are there which is having the different antennas. Now the output of each of this branch is applied to different weights. Now the weights are being controlled by, so there are 10 branches, 10 weights I am going to consider. The value of these weights will be controlled by this cophase and sum block. Now output of this cophase and sum block will be considered as an output, the final output that we are considering. So this is less complex as the selection diversity technique, and the idea will be is been discussed in there. So there is a kind of thing is been there that there is a kind of weighting functions that has to be considered using this branch weight work. Now next one is the maximum ratio combining. So in this case, maximum ratio for noise limited systems without interference, MRC results in the best signal to noise ratio. So here all the incoming signals from the M branches are weighted according to their individual signal voltage to noise power ratios, and then these are added together. So what it says that again I am taking the same example, let m is equals to 10. So there are 10 different branches are there. The output of each of these branches is being multiplied using different weights. So there are W1, W2 up to W10. So 10 weights will be there. Now the output of these 10 weights will be applied to this cophase and sum block. Now these are the branch weights. Now the output of this branch weight will be applied to this detector. Now the feedback from this detector part is given over here by to control this cophase sum block and to control these weights value, so that the proper kind of weights can be selected, and then the output will be done. So all the individual signals, so whichever value, whichever branch is having the highest signal to noise ratio, it will be connected over here. So all the individual signals must be co-phased before being added together. This requires an individual receiver circuitry and a phasing circuit for each antenna element. So it produces an acceptable signal to noise ratio compared to the other techniques. So this is the maximum ratio MRC technique which is being used over here. Now next one is the spatial diversity and multiplexing in MIMO systems. So we have discussed this diversity. Now comes the MIMO system, how this diversity or multiplexing technique will be used in MIMO system, that is multiple input, multiple output. Now you can consider this channel here. There are different multiple inputs are there, then multiple output will be there. So single input, single output will be there, means no diversity is required. So this is not the case, means 1 to 1, one transmitter, one receiver will be there. Then single input, multiple output. So one transmitter and more than one receivers will be there. Multiple input, single output. So this will be the receiver, this will be the transmitter. Last one is the multiple input, multiple output. So n number of transmitters, n number of receivers. This is the case. So these are the 4 different types of antenna systems that we can consider. Other than that, there is no possibility. So comparison of channel capacities of various multi antenna systems are there. Now this particular slide is going to give you a formula to calculate the channel capacity, which is given by Shannon, which is a very famous formula to calculate the capacity of the system. Now this formula can be changed depending on the different depending on the number of transmitters and number of receivers. So here we are considering n number of transmitters and m number of receivers we are considering. So this will be fixed, means how many number of transmitters and receivers are there. So you can see in case of single input single output, we are not considering the case of SIS, so that is single input single output. In that case, m will be is equals to 1, n will be is equals to 1. But when we are considering this single input multiple output, means m number of receivers are there, so this signal to noise ratio will be multiplied by m factor. This is the common formula. Capacity of the channel is equals to bandwidth multiplied by log to the base 2 1 plus signal to noise ratio. Generally this is described means this is been described in terms of decibel only. That is the main unit that we are considering for signal to noise ratio. Then this formula can be changed when we are considering the multiple input single output case. In that case it will be considered as n. Next one is MIMO, that is multiple input multiple output. So n number of transmitters, m number of receivers are there, so this signal to noise ratio will be multiplied by m into n. So that is the case, and W bandwidth will be same in all the cases, so that is bandwidth. Now next is introduction to multiple input multiple output systems are there. So multiple MIMO offers greater spectral efficiency as compared to SISO, SIMO, MISO systems, higher data rates, greater range, increased number of users and enhanced reliability. So this is the introduction of MIMO. What do you mean by MIMO? In this case, MIMO system consists of several antenna elements, means at the transmitter side there are multiple antennas will be there, at the receiver side there will be multiple antennas will be there. So which means multiple input multiple output system is there. So it consists of several antennas plus signal processing at both the transmitter and receiver has been there, and spatial multiplexing in MIMO. The underlying mathematical nature of spatial multiplexing MIMO, where data is transmitted over a matrix rather than a vector channel. Why we are considering matrix? Because there are n number of transmitter and m number of receivers are there. It is not a vector channel where there is only one transmitter and more than one receiver is there. So that's how we can generate a matrix depending on the number of users that are using the channel. It creates a new and enormous opportunities beyond just the added diversity or array. Again, benefits the spectrum efficiency, which means that if I am going to combine n number of transmitters and m number of receivers in a particular diagram, then it can be combined using different number of channels, mean more than one channel will going to use a common more than one user can use a common channel, and that this will definitely going to increase the efficiency of the system that is considered. Next is spatially multiplexed MIMO system. So this is the diagram which is showing that let's say this is a MIMO transmitter, this is a MIMO receiver is being there, and this particular diagram is showing that the correlation between the different points will be there. Now you can see over here, this is modulation and mapping will be there. So different types of users are there here. This is having this number of bits, this is having this number of bits, and these are being modulated and mapped together, and it will be combined to different antennas like A1 to A3. Now these are the signals which has been transmitted, and it will be received by a signal processor at the receiver side using 3 different antennas, and the output of this will be applied to a filter. So this is the MIMO receiver. Now you can see that this is a very simple type of keying technique, that is ASK technique, has been used. So this is how the relationship between the different parameters will be there. So we send multiple signals, the receiver learns the channel matrix and inverts it to the inverts to separate the data. Now next is the MIMO channel model is a matrix in mathematical form. So this is the matrix that we have considered. These are the different antennas. Now you can see that H parameter matrix will be drawn over here. So these are the number of inputs, these are the values that has been considered over here. So this constitutes the output plus the noise. So if you are going to multiply this H11 means this is the H matrix. So if you are going to combine this particular value and multiply and add together by these weighting functions and add it to the noise, then this particular matrix will be generated. So H is the complex channel matrix over here, and here to calculate this approximated value, this means when we are considering this B cap value, B is the original, B cap is known as the predicted value. This is known as the predicted value over here. Now this predicted value is denoted by this cap version, and then if you want to calculate this, so definitely you have to calculate the inverse of this H matrix and then multiply it with x1, x2, x3. These are the parameters of the input matrix. Now this is the noise which we are considering over here is the AWGN noise. So what is AWGN noise? Its full form is additive white Gaussian noise. Now this additive white Gaussian noise, why we call it so? Because it is additive in nature, means it will be definitely added. It is not a multiplicative noise, because if some signal is being affected with multiplicative noise, then its characteristics will be changed at an exponential rate. Next, why we consider Gaussian? Because the transformation and inverse transformation of this particular signal will be a Gaussian function. Now next will be it is a kind of noise only. So this is the signal noise that we generally consider in our communication system. Now when we draw its PDF, that is probability distribution function, so it will be constant from minus infinity to infinity, and its value will be n naught by 2. So that is a constant value that we consider for this AWGN channel, that is white Gaussian noise channel. These are the references that you can consider for this particular topic. Thank you.